G'day, in this video we start module 3, which is all about waves and thermodynamics. While waves covers the major portion of this module, and it does come first in this syllabus, we're actually going to be looking at thermodynamics first. And in this video today, we're going to be covering some of the core basics, most of which will be a revision to you. Core concepts that we're going to be looking at, as implied by the two components of the word thermo and dynamics, is that we're looking primarily at heat and energy and the work that can get done as a result of that. So today we're going to be covering concepts which help us to understand and unpack dot point 3.5.1, 2, and 4. We're looking at module 3, waves and thermodynamics, and the fifth and final inquiry question, which is how are temperature, thermal energy, and particle motion related? Again, here, the key pillars of what thermodynamics actually is. So some key ideas that we're going to be focusing on is the relationship between temperature of an object and the kinetic energy of particles that are in it, the idea of thermal equilibrium and what it is, as well as how energy through heat can be transferred through conduction, convection, and radiation. So our key learning intentions, first we're going to review the concept of particle theory and reflect primarily on how temperature is expressed within the particle model. Also going to be looking at thermal equilibrium and unpacking some key concepts and misconceptions around that, and then finishing off by looking at our methods of energy transfer. So first off, when we look at particle theory, it's important to, revise and conceptualize the idea that all matter is made from atoms, and depending on the state, depends on how those atoms are arranged, how they behave, what they do. But a really key and important point to really focus in on as well is that the motion of particles, or the energy that particles have, is dictated by their temperature. If they're at a higher temperature, it means that those particles have more energy and thus move faster. If they are cooler, then that means that the energy of the particles is less and they move slower. This sort of relationship can also be seen simply through the expression of how atoms behave as different states of matter. Something to always consider is that particles, whether they are as a solid, liquid, or gas, are constantly in motion. So in the case of a solid, while they are in a fixed position, they will vibrate on the spot. And then for liquids and gases, we call these fluids because they have a higher degree of free motion. For gases, they can move freely in all three dimensions. And for a liquid, while they do collect and sit at the bottom of a container that they are in, they are free to be able to roll and move past each other. Something else to consider is essentially there is no matter between atoms. Atoms is what constitutes all of the matter that we have in the universe, and any space that is between atoms is considered to be empty space. It's not like there's air between those spaces or anything like that. There is no matter, there is nothing in between. A little bit more on states of matter, we should be familiar with the idea that gases can turn into liquids and vice versa, liquids to solids and vice versa, but also solids can turn into gas and vice versa, and these are what we call our state changes. Most of the time we see and experience evaporation and condensation, as well as melting and freezing as pairs, which get us from solids to liquids and then liquids to gases, or the reverse way around. Generally speaking, for most substances, we find that as we increase heat, the particles gain more energy and go from solid to gas. And as we reduce heat, those gas particles will begin to condense, then freeze into a solid as those particles have less energy. However, it is important to, acknowledge that with those heating and cooling methods that we have, there are some rare examples where solids can turn immediately into gases without the liquid phase, and vice versa. We call these processes deposition and sublimation. An important thing to note here too is that when we're looking at the properties of matter, we can describe different substances by their melting and boiling points. Each substance will have a different temperature at which they melt and at which they boil. And these are the temperature ranges where we will see significant change of state rather than change in temperature. There is a PhET simulation which visualizes a lot of these things in terms of the behavior of particles as well as their state changes. This might be something that we look at in class time. So we've been alluding to this idea that temperature is quite closely related to the energy present in particles. However, we do have three general temperature scales that we usually work off. They are Celsius, Fahrenheit, and Kelvin. Celsius is definitely the most commonly seen temperature scale, certainly in most places in the world. It's generally seen as our everyday scale to measure temperature. Fahrenheit is quite similar, but is not used in many parts of the world. Mostly it's used in the US. It's not a temperature that we will be reflecting on really at all in the scope of this course. And the last one there is Kelvin, which is a measurement that gets used quite a lot in the sciences. And I want to unpack this idea of Kelvin and how it's similar and different to the other temperature scales, as it is a scale of temperature and a unit of measurement that we will start to use within the scope of this course. Something to keep in mind, and this is one of the most important things, that changes to temperature in Celsius in Kelvin are always equal. If you increase temperature by 1 degree Celsius, you've also increased temperature by 1 degree Kelvin. Similarly, if you increase the temperature of an object by 20 degrees Celsius, it will also increase the temperature of an object by 20 Kelvin. In other words, what we can say is that the change in temperature in degrees Celsius is always equal to the change in temperature in degrees Kelvin. However, it is important to note that temperatures measured in degrees Celsius are not equal to temperatures measured in degrees Kelvin. And that can be seen here at the freezing point of water. The freezing point of water in degrees Celsius is 0 degrees. However, the freezing point of water in Kelvin is 273.15 degrees Kelvin. So if we were to take water up 1 degree from freezing, then that would mean that the temperature of the water would be 1 degree Celsius or 274.15 degrees Kelvin. Now what that means is the difference between the temperature measured in Celsius versus measured in Kelvin is always going to be 273.15 degrees. In another example, if the temperature is 0 degrees Kelvin, that means that the temperature in Celsius is negative 273.15 degrees. Or if the temperature in Kelvin was 373 degrees, then the temperature of that water at that stage would be 100 degrees Celsius. Again, a difference of 273.15 degrees. Now, the major reason why Kelvin is a preferred measurement in science is because there are no negative temperature values in this case. We always stop at 0 degrees Kelvin, which seems a little bit odd. I guess you're probably thinking, well, why don't we just go colder? Why can't we have negative 1 degrees Kelvin or lower than that? And that is because of this concept of absolute zero. When we talk about absolute zero, we are referring to a temperature at which nothing can get any colder. And the reason is actually shown in this animation here. At 300 degrees Kelvin, which is about room temperature, we see that the particles are moving because they have energy, but at 0, they stay completely still. At 0 degrees Kelvin, at absolute zero, we cannot get any colder because at that point, the particles do not have any more kinetic energy in them. Thus, you can't reduce their energy any further. Another concept that I want to cover today is the idea of thermal equilibrium. Essentially, when we're looking at thermal equilibrium, we're focusing on the transfer of heat energy to an object with less heat energy. In other words, heat always flows to a colder place. And that can be done through conduction, convection, and radiation, concepts that we will be going through in more detail shortly. Something that's really important and a misconception that we don't want to hold is the idea that cold is transferable. Cold is not transferable. Cold objects will absorb thermal energy from hotter objects, but you can't transfer cold into an object. Essentially, what you're doing is you are reducing heat energy in an object that cools down, meaning that that heat energy is going somewhere else. It's being transferred to another place. So in scenarios where we do have two objects that are able to transfer heat to each other in some way, shape, or form, which are not the same temperatures, is that idea of heat energy being transferred into a place where there is less. When we hit thermal equilibrium, what that means is that the heat, the temperature, the energy, the thermal energy of both objects are now balanced and equal. There is an assumption that we can make with thermal equilibrium as well, and that is that even if, say, an object A and C are not touching each other, we could predict that they are the same temperature. And that would be the case if we were to achieve thermal equilibrium between A and B, and thermal equilibrium between B and C. So in this instance, let's say that we knew A and B were in thermal equilibrium and they were both 25 degrees, and we knew that B and C were in thermal equilibrium and they were both 25 degrees. That would also mean that A and C are in thermal equilibrium as well. And this is a way that you can ensure that two objects are in thermal equilibrium without actually having them in contact with each other. In other words, having a middle medium which is able to synchronize the temperatures of A and C and ensure that there is thermal equilibrium between all of the substances. An assumption that we could make, assuming that A and C are in equilibrium, is that if we were to bring both of those objects together, there wouldn't be any more heat transfer or temperature changes because they are already, as we said, in thermal equilibrium. But how can objects get to thermal equilibrium? Well, that is through methods of thermal transfer. That can either be through conduction, convection, or radiation. So conduction, we see the transfer of energy between molecules that are close to each other. For convection, we're looking at movement of fluids, so liquids and gases, when they get hot or when they get cold. And then radiation is a form of electromagnetic radiation. That is a key part of our waves topic, but we will go through the thermal radiation basics in the scope of this inquiry question number 5. So first off, conduction. Essentially, if something is able to conduct heat, a heat source is going to be providing heat energy to some of the particles, increasing their vibration. What that will lead to is more frequent and higher energy collisions between particles. And these collisions will transfer their thermal energy from a hot place to a cold place, in other words, through the substance. So as a visualization, what we can see in this animation is that particles here at the start get lots of vibrational energy, and as they become more and more excited, they gain more energy. They're able to transfer that energy through collisions to the other particles which they are next to. And we see that heat energy slowly moves through the entire object. This is an example of conduction of heat. So when we're looking at convection, we're looking at fluid particles, liquids, and gases which are free to move. The hot fluid particles are able to rise, and the cold fluid particles are able to sink. And what we end up with is this circular pattern of a convection current, where warm substances will rise and cool substances will sink. This doesn't work in a solid because our particles are sitting in fixed positions. However, for fluids like liquids and gases, their free movement enables this to happen. Generally speaking, we see convection currents because warm matter is less dense than cool matter. Thus, the less dense things rise and the cool things sink. This can be visualized in a couple of these animations here. What we can see in this first animation is that the gas particles which are around a fire are undergoing convection currents, that as they get close to the flame, they begin to warm up and rise. As they move away from the flame, they cool down, at least become cooler compared to the particles down the bottom, and begin to sink again. We end up forming these circular currents of particles, and we go through this continuous rotation of particles around the fire. Similarly, we can sort of see the same idea here in this experiment where there are some food dyes at the bottom of this liquid, which is giving us a visualization of what the particles are doing. Essentially, they are rising in the center here where it is hottest. They're then able to move outwards across the liquid. Over here in these pockets, they'll begin to cool down and begin to sink as well. That can be hard to visualize in water using food dye, but you can sort of see some wisps at the bottom moving in at least a diagonal direction as they begin to sink back down. Our last method of heat transfer here is radiation. Again, electromagnetic radiation or wave energy is something that we're going to be focusing on for a large portion of this module in significantly more detail. Here we just need to revise the idea that there are many different types of electromagnetic radiation, but the infrared waves are the ones that are a part of the spectrum which are associated with this concept of heat. So when we start to look at objects that radiate, most common or notable one being the sun, that's the only way that it's able to transfer energy to us on Earth. Or in general, objects with any kind of thermal energy will release heat through radiation as well. When we look at these examples, the key focus here is that electromagnetic radiation is able to transfer from one object to another, not necessarily with any material medium. And this is unique compared to conduction and convection, which both require the motion and movement of particles to transfer energy from one particle to the next, or to transfer energy throughout an entire system. Here it's easiest to see when we reflect on what we know about space, and that space has next to no matter, meaning that this thermal energy is able to transfer from one place to another without matter as a medium for that energy to move through. Thank you very much. In the next video, we're going to begin to look at the concept of specific heat capacity. And this is something that we can do to measure the capacity of a substance to be able to take in or transfer heat. There's some mathematical relationships which we will begin to unpack so that we can do some practical work, take some measurements, and then be able to do associated calculations with that. Until then, have a good one.